Hey everyone, it's Miss B, and in this video we are looking at Unit 1, Lesson 11, the cumulative practice problems for illustrative math geometry. So let's start with our first one here. So this one's asking us which of these constructions would construct a line of reflection that takes the point A to point B. So we have 2 points. We want to construct a line of reflection between them. And this image is unrelated, so I'm trying to keep that off the screen, I guess, but my whole question here. We have 4 options here. Construct the perpendicular bisector of segment AB. Construct a line through B that's perpendicular to segment AB. Construct a line passing through A and B, or construct a line parallel to line AB. Well, I know that with a reflection, my point should be an equal distance on either side. So if I have A and I have B, I should have an equal distance between those 2 points and my line of reflection. So, and that's the closest thing we're going to have to that is the perpendicular bisector, because that's going to be the shortest distance to the line and maintain that it's equal on both sides. So our answer here is choice number 1, construct the perpendicular bisector of segment AB. Now for question 2, this is where the drawing comes into place here, line L on the right. So a point P stays in the same location when it's reflected over line L. What can you conclude about P and show how you know? Well, I know that a reflection maintains the distance that a point is away from the line, it just moves it to the other side. So if it's not moving, that means there's only one place it could be, and that means it has to be on the line. The only option we have is for it to be on the line. If I had a point out here, I would have to reflect it across and have it be over here. So we'll say P is here, and then I can call this like A and A prime. So for my explanation, I can say P must be on the line of reflection. And then we can say otherwise, oops, maybe I should write legibly. Otherwise, it would move from, I'm going to say otherwise it would move from one side of the line to the other. And then I'm going to say example A to A prime. That looks more like a comma. A to A prime, also because the symbol should be up here. I'm going to say A to A prime on the picture because I drew it. So the only place for P is to be on that line. Otherwise, it would move like A to A prime and switch from one side to the other. Okay, question 3. Lines L and M are perpendicular with a point of intersection P. Noah says that a 180-degree rotation with center P has the same effect on points in the plane as reflecting over line M. Do you agree with Noah and explain your reasoning? Well, first off, they did tell us that the lines are perpendicular. We're also given this here, and so I'm going to highlight that I have my little perpendicular in the corner over there too. Now, a reflection across a line is like creating a perpendicular bisector, or a perpendicular bisector existing, and if we had one point, we would then be creating our other point. So if I had a point here, I would be creating a perpendicular bisection of it. It's okay, just making sure I was using the right line. It is line M. So we would be creating the segment that would be perpendicularly bisected by M. Now, he's saying that a 180-degree rotation with center P would have that same effect. And I disagree. So I'm going to show you with a point that's in here, like in one of these spaces. If we had something that was on line L, then Noah is going to be correct because it's going to take this 180 degrees over to the other side and create the perpendicular bisected segment along line L. But line L is the only place that that's true. So I'm going to use my red pen here, and let's just put a dot. Let's put a dot here, just smack in the middle. I'm going to call this A. Now, if I take A and I reflect it across, we're going to have it here on the other side, a little bit lower than that, so I'll move it. Oh, there we go. So it's going to be reflected, and it's going to end up in this position, so I'm going to call this A prime. If A was rotated, we would be instead maintaining its distance from that center of rotation and creating a 180-degree angle down here. Now, this I would call, I'm not going to call it A prime because it's not an actual transformation that we're doing. I'll call this B. So I'm going to use this to explain my reasoning, and I'll use the laser pointer tool so it doesn't stay on my document, but I can still show you. So a reflection would move it across line M, creating that perpendicular bisector. But this one, we would rotate, essentially this whole line would rotate 180 degrees. And it would have to maintain its distance from point P here. So that's what we're going to put in some words. So, how best to word this? We can say no, or we'll say Noah. I do not agree with Noah. Because a reflection would take a I'm going to say the reflection would take I'm using this diagram as part of my explanation, so, and that's fine if you're drawing a picture. So a reflection would take point A to A prime in my diagram. And I can say A prime would be perpendicular bisected by line M, and then I can say a 180-degree rotation of point A would take it to point B in my diagram, or in my picture, either way. So I don't agree with Noah. The reflection would take it across, but still leave, in this case, the vertical position of A in place. Whereas rotating 180 degrees would take it an equal distance from P, but not perpendicular. It would actually have to pass through point P. So if you chose to describe this without a picture, it would be a little more difficult, but we could say Noah is not correct because the only points that would have the same effect are on line L. And we can actually add that in. Let's add that in at the bottom. The only points which would map onto the same image after reflecting across line M or rotating 180 degrees around point P would be points located on line L. So this part isn't entirely necessary for your explanation, but I think it's kind of key to how I picture this because that was part of the explanation I gave you. I just used my laser pointer and I didn't really show you or keep it as part of my diagram, but we might as well include that in our description. So sorry that was a little long-winded. I actually was pausing a little bit to best think about how to state that. So let's move to question 4. So question 4 is some multiple choice here. We have 4 triangles that have each been transformed by a different transformation. Which transformation is not a rigid transformation? So I know that a rigid transformation is either a, let's see, rigid transformation, I'm going to underline this. And those are 3 options: translation, sorry. A transformation is a transformation, go figure. A translation, a rotation, or a reflection. And I like to think about those as slide, spin, or flip. So we're going to look for those movements here. A is a translation because we're just sliding that shape. B over here is actually going to be, it looks to me like a reflection across a line. So we can say this is reflection. C, well, it's not a translation. It's not a reflection. It's not a rotation. This one would be called a dilation, but we can actually say that this is our answer. This is not a rigid transformation. But we're going to confirm with D that this would be a rotation. And generally, that would, yeah, rotate. We're rotating sort of this direction, so this is our rotation. Now, if we're just looking at it, part of being a rigid transformation is that it's going to preserve the size and the shape of the image, or I'm sorry, of the pre-image when it maps it onto the image. In this one, the size is not the same in the image as it is in the pre-image, or you can write that in a shorter way and just say the size changes. But I wanted to throw in some of those academic vocabulary, mathematical words. So yeah, explain how you know. The size is not the same, and I then labeled my other ones because I do know that those ones are based on the types that we have. So next question we have here is number 5. So this is telling us that there is a sequence of rigid transformations that takes A to A prime, B to B prime, and C to C prime. Then the same sequence takes D to D prime. We want to draw and label D prime and show how we got D prime. So I'm going to use red to make my color stand out a little bit. It does kind of look like this might just be a little bit of a rotation and maybe a translation, but D is kind of this distance away from C, so I want to make sure that my D prime is that same distance away, and yeah, so we can show like C to C prime, D to D prime. They're going to follow that same path, but because there's probably some rotation involved, B and B prime and A prime are going to look a little bit different unless we know where the center of that rotation is. Plus, they just told us this was a sequence, so there's probably more than one. But what I can write for my explanation is that D prime should be in the same relative location, or we can say same location relative to C prime as D is to C in the pre-image. Basically, since no parts of this shape should really be stretched or anything like that, I'm going to have D on this side of my triangle, which is AC, and it's going to be that same distance from C. So on my new triangle in my image here, which is A prime C prime for this segment, D prime should be that same distance away and lie on that same segment. Okay, and we're almost done with this assignment, but I believe we have, oh, nope, we're actually done with this assignment. I thought we had one or two more questions, but we're actually leaving it there. So that was Unit 1, Lesson 11, the cumulative practice problems for illustrative math geometry.